Good afternoon, everybody. Thank you very much. Yes, I'm going to share results regarding manure or slurry cooling on gas emissions during fattening. The study was conducted by Ifip in collaboration with the Brittany Chamber of Agriculture in Ariane MSAS within a project called Temporales, the results of which I shared last year, funded by ADEME within a call for projects launched by COTIA. About the context, France has committed to reduce its greenhouse effect gases and ammonia emissions, and pig farming is a small contributor to these two gases. France still wants to reduce its emissions. A number of techniques have been used, and some of which were assessed by other member states, especially northern European countries. And this has led to a number of questions regarding their efficacy and applicability in our French national operating conditions. This is the case of slurry-based heating based on catching calories from slurry, cooling it down, and using the heat to provide energy and have an action on slurry temperature. Temperature, like pH, is one of the predominant factors for the emissions of ammonia. And so by cooling the slurry down, it should reduce ammonia emissions. At least that is what is claimed by some Danish publications. What is this heating system? It's a network of tubes which are placed at the bottom of the slurry pit. And in these tubes, a heat transfer fluid is circulated, catching the calories from the slurry and bringing them into a heating system to preheat the air in the farrowing pens or post-weaning pens. And we looked into this technique in order to understand whether it was efficient. And we started with an initial study in experimental conditions within experimental stations in Romillet. And we had control rooms, 54 pigs, between 30 and 118 kilograms on integral statted floor. The slurry is stored in the pit during the whole presence of the animals. Ventilation is conventional. Fresh air comes through the roof and is extracted under the statted floor. The setting for the temperature is 22 degrees, and the animals are fed with a biphase feed, a conventional feeding strategy with a growing feed and a finishing feed. We then compared the control room with another system where they used a bottom of the pit heating system. 30 meters of tubes were placed directly onto the bottom of the pit, filled with a heat transfer fluid, 33% glycol, and the installed power is 20 watts per square meter. Another system for slurry-based heating was tested. It's a surface heating system. We built a sort of raft on which we have attached the tubes, and the raft is floating on the slurry, and it raises as the slurry level raises. Now, the technical characteristics of the surface systems are identical to the ones used at the bottom of the pit. In parallel with the experimental conditions, we also wanted to test the efficacy of this heating system based on slurry, and we had a look in a farm in Vendée, 2 rooms, one the control room has the same conditions as the experimental room in our study, except that only the bottom pit heating technique is tested in real-life farming. Here we had different conditions regarding the number of environmental parameters as well as weighing the pigs and weighing the feed. We measured the volume and the composition of the slurry, and we also measured the concentration in ammonia, nitrous oxide, and the methane with an infrared system within the ambient air every 3 minutes. We measured the ambient temperature as well as the slurry temperature at the bottom of the tip, and we followed the ventilation flow in order to calculate the gas emissions. Let us look at the results, starting with the zootechnical performances. Here we have the animal performances in the experimental conditions, and it appears they are greater than the average values provided by GT Porc in 2023. We have significant difference for the daily weight gain of animals raised in the room where the heating system was at the bottom of the pit, with also an increased daily weight gain in the end of the finishing period. The other parameters, we saw no significant difference. Regarding performances in the breeding conditions, we were not able to use the parameters for daily weight gain and conversion index, but we have something that is quite equivalent between the two different systems tested in a real farm. Ambient temperature, 25.6 degrees, and you see that the temperature in the bottom of the pit heating system in experimental conditions is lower, and significantly lower, whereas in the room where the heating is done with the surface raft, there is no difference. The setting of the temperature is 22 degrees, and we get a significant reduction only for the ambient temperature in the experimental room with the heating system at the bottom of the pit. But we have no difference here between bottom of the pit heating system in breeding conditions on the ambient temperature. Now, things are very different for manure and slurry. Here you see that the slurry temperature in the experimental conditions in the room where we have the heating system at the bottom of the pit is 14.5 degrees, so 10 degrees less than the ambient temperature. This is a significant difference if we compare with the ambient temperature in the control room. The same goes for the surface system, and this is 7 degrees lower than the control room, so it's significant as well. It means that both systems for slurry-based heating are functioning, and the idea is to decrease the temperature of the slurry, and it works. We do decrease the temperature. And in a real farm, what happens is that the temperature decrease is not quite so marked. It's slightly higher in the bottom of the pit heating system, but not quite so marked. Let us see what happens in the environmental parameters. The control room, 2.2 kilograms of nitrous oxide per slot and per year, which is consistent with the values provided by the literature and the data obtained in similar conditions in previous studies. But we do observe a reduction, approximately 20%, of ammonia emissions in the pen, which is equipped with the bottom of the pit heating system. In breeding conditions, again with bottom of the pit heating system, we don't have an effect on the breeding conditions. Now, if we compare the control room with the room equipped with the heating system on the surface of the slurry, there is no apparent effect reconducible to the surface system regarding ammonia emissions. So reducing the slurry temperature is an important parameter in order to reduce emissions. And if we look at the literature, we find some studies, especially Hansen et al. 2013, they establish a relationship between the power of cooling installed and the reduction of ammonia emissions. They claim that we have a 10% ammonia reduction per 10 watts per square meter. Now, in experimental conditions, we have 20 watts per square meter, which is a 20% reduction. That's what we measured. And in breeding conditions, the power of the cooling is only 10 watts per square meter, and therefore, according to the same equation, we only get 10% of decrease. Holm et al. In 2016 came up with a different equation, but with similar results. The reduction rate is slightly greater, but still within the values that we obtained. In breeding conditions, there was no decrease. But if we calculate the variability of these parameters and the uncertainties of measurement with a 10% variation is a bit of a challenge. Let us look at nitrous oxide. Emissions are 0.08 per slot and per year, which is slightly low as a value in the literature. In experimental conditions, no difference. It does not seem that slurry heating systems have brought any difference. And we could not measure the nitrous oxide difference. Methane, which is definitely the most interesting parameter in this study, in the experimental conditions in the control room, it's 4.3 kilos of CH4 per slot and per year, which is consistent with what can be found in the literature. Whereas in breeding conditions, we rose to 13 kilos per slot and per year of emissions, and we could not come up with any clear explanation to explain this increase. The breeding conditions were quite close to what we applied in the experimental conditions. And if we compare the control room and the emissions from the control room and the one with the slurry heating system at the bottom of the pit, the reduction is close to 60% of the methane emissions in experimental conditions. In breeding conditions, the decrease is 20%, 19%, but still there is a decrease. And if we go on to compare the control room emissions with the emissions in the room where the system is on the surface of the slurry, the decrease is 40%. Roughly, in experimental conditions as well as in breeding conditions, bottom of the pit slurry heating system obtains a 20 to 60% reduction of methane emissions, reducing the mesophyte flora in cold conditions. And this is directly reconducible to the slurry cooling, more efficient in experimental conditions because there is a direct link with the cooling power installed. In conclusion, slurry-related heating is not quite as efficient as we would have hoped for ammonia emissions. We have calculated that there is an impact with the cooling power installed. So based on Holmes' equation, if we went to 40 watts per square meter instead of 20, we would have a 40% reduction in ammonia emissions. However, with a 20 watts per square meter cooling power, we did achieve a significant decrease in the ambient temperature, and this would in turn reduce the temperature in the slatted floor, and we might be able to improve the comfort for the animals and improve the performances. If it was very difficult to prove any effect on ammonia, we do measure obvious effects on methane emissions, and that obviously is very interesting if we talk about the low carbon strategy. Presentations before mine have shown how important it is for us to find solutions to reduce our greenhouse effect emissions. But the presentation does not go into the reduction of the cost of energy, but the idea would be to catch the heat, to reduce our energy consumption. But this is not easy to apply to existing buildings because you have to install the tubes at the bottom of the pit, which means that you have to then put some concrete, and that decreases the storage volume, and it's a high price. And there are questions regarding maintenance of the system. When things are buried in concrete at the bottom of the pit, there is always a danger of porosity, leaks, and what can you do at the bottom of the pit? However, this heating system is applicable in our national production systems. The efficacy could be improved for ammonia emissions, but still is not to be disregarded as far as methane is concerned, and methane is a greenhouse effect gas, so it needs to be taken into consideration. Thank you very much for your attention.